as you heard, my name is Marija. So I'm coming from the Institute of Physics Belgrade, and I'm actually associate research professor at Scientific Computing Laboratory. But I'm also a head of innovation center at the Institute of Physics Belgrade. So I'm heading our collaboration between industry and science. But this talk will be actually what I'm doing as a researcher and as a scientist. So this is a nice picture of our institute. This is the most important thing that we have as a resource at the institute. And you may wonder why physicists have any connections with data science, but actually, to be honest, all of these things are collecting the data that need to be preprocessed, cleaned from the noise, and analyzed to find the leading or driving mechanisms that drive different kind of systems that physicists typically study. We also have interesting thing going on at the Institute of Physics Belgrade. So this is a Teslagram technology that originates from the institute, and actually my innovation center is working on this, and data science also has a lot of influence on this. I'm coming from Scientific Computing Laboratory, and we actually do things a little bit different. So we don't do these kind of experiments. We do simulations, and we also do a lot of data analysis. So my group works on social systems. So we are physicists working in a field called computational social science, and our resources are behind group of people that are shown here. Why I wanted to talk about this today? So most of you here in the past 2 days and in the conferences that are organized also in Belgrade talk about machine learning, talk about artificial intelligence, and yes, it's driving the world. It's a quite important resource. We depend on it a lot. So as you can see, it's changing the world. It's changing the way we are thinking about different kind of stuff. So starting from recommendation algorithms, how we buy, how we read, how we watch different kind of videos and stuff. Of course, image recognition. It's very, very present in health. We learned about this a lot in the past 2 or 3 years when we had these huge pandemics. But we also, so our group is also quite interested in autonomous driving and how we can actually help with this, knowledge organization, and so on. You heard today that AI also raises a lot of questions. So ethics is one of them. The second one are biases. I very often follow research done by my colleagues from computer science who actually study biases, and biases can be quite problematic, and we also see a lot of misuse and abuse. Why these kind of things are happening? So misuse and abuse, not that much related to data, but actually things related to ethics and biases are typically related to data. So AI is quite strongly data dependent, and it's quite powerful, but it's not without problems. So it makes a lot of mistakes. We all know that it's a black box, basically, so we don't understand how the AI actually learns from the data, how they use this knowledge that they learn from the data to predict certain kind of things, and definitely does not provide us the mechanisms that are actually behind the systems that we're trying to understand and predict. And this is quite different from the things that we see in physics. So in physics, yes, we measure, yes, we have a lot of data, but we actually try to understand these systems on basics levels in order to be able to predict them. So this is where we actually have to think about to combine artificial intelligence, so machine learning, deep learning, and so on, with some more traditional approaches that maybe may help us to actually understand these kind of systems. So I'm coming from actually a field which is multidisciplinary field. It's called computational social science. It's, I would say, quite new in some sense, but actually now already not that new, okay? So it exists for the past 20, 25 years, and actually this ICT, so information communication technologies, were driving a lot of this field because finally we got the data about social systems and we could actually study them. But what we saw in this computational social science is that this is not something that just social sciences can do, or this is something that actually physicists are quite interested in. So what we usually offer are these abstracted models and methods actually to analyze these data. Of course, colleagues from computational, computer science and data science that provide tools to actually study these large-scale data sets, and definitely colleagues from social science that can help us to understand better and interpret these results. So this is an example of a social system. What is in the basis of any social system, even this one, these conferences, any place, is that it consists of large number of people that interact with each other, okay? And what also happens is that all social systems exhibit collective behavior. Pandemic is a collective behavior. Opinion dynamics is a collective behavior. Spreading of news and information is a collective behavior. Whenever you're on any online social media, this is a collective behavior. You are not able and capable to isolate yourself from the rest. You're always influenced. Your opinion, your attitudes, your way of seeing the world, what you share, what you see, everything is related to other people that interact with you. So basically, social system is a type of complex system, and this is something that physicists are quite well aware of, and complex system started from the physics. The center of this is actually the structure of this social interaction, okay? And while social sciences typically are interested in specific features and knowledge and behavior of individuals, physicists typically tend to forget about this and look at the structure and actually search for universalities and some specific social laws that we can actually understand from our analysis. So what we try to do and what our goal is to determine and understand the principles that govern this collective behavior. And we have many means and many ways how to do this. So usually we use tools from statistical physics, from computer science, from complex network theory to understand and measure collective behavior in this empirical data. And then, because doing experiments with people is usually quite complex and very, very prone to biases, we typically use theoretical models to capture some of the mechanisms that we consider as an important for these collective dynamics, and actually to test our theories. And the cluster that I show is kind of invaluable resource in this. If you look, so what is the focus of this talk for me is to actually this universality. So whenever I speak with people from computer science and from data science, but mostly from industry, they focus on individuals and they want to, as better as possible, predict the behavior of a certain individual and what are the needs and wishes of that person, okay? But you have to understand, when it comes to collective behavior, this behavior has these universal patterns, okay? This means that the patterns that we see there can actually be very similar for very different systems, and they can transfer to time periods, okay? So some things that are happening like 20, 30 years ago are actually very similar to today. This we saw actually in several of our systems that we studied. The most interesting one for me was voting behavior of people, where we actually showed that when you have rules or the election rules determine how people will behave, not culture, not time, not history, not, I don't know, political parties or something like that. So basically what we showed that the same thing you see in Finland, who has a very stable democratic system, the same thing you see in Italy, who has this kind of different kind of changes in voting rules. So whenever they had the same rules as Finland, they had the same patterns. And in Poland, who actually was a communist country and didn't have any kind of democracy until 90s, and now they have actually very similar behavior. We also see these voting, the think patterns that we see in voting. We also see in citation patterns in science. In mobility patterns, it's quite interesting because actually we see mobility as something that is kind of hard to predict, and there are no universal patterns, but this is actually not true. There's a lot of laws that govern mobility in cities and between the cities, stocks. In history, we also see a lot of universality, and also in biological systems, not just the social ones. So these universalities are something maybe that you should think about when you study your data. Maybe you don't have to analyze like large amount of data. Maybe you can find some universalities in your patterns so you actually can work faster and more efficient. What is the most important thing? So physicists know about universalities for more than 70 years, okay? And what universality means, it means that the structure of interactions is what is important, while the information or specificities of elements that interact with each other are not that interesting, okay? Or they don't influence the collective behavior. And this leads us to this structure of interaction network. So basically, in the social system, central law is a social network, okay? We want to understand the structure of this system, how the structure of this system influences the behavior of, so how the structure of social network influences the behavior of a system, and we want to understand how this structure evolves and how it emerged from the beginning, okay? And we know from different kind of real systems, offline, online, and from different kind of models, that actually the structure of a social system and its function and dynamics are inseparable. They're very strongly connected, okay? And complex networks or social networks, they're actually everywhere. This is the brain, this is a social network, this is a network of words, this is the airport network. So you can find it everywhere. And if we go into biological networks, actually we see that people, we combine social networks, so we are part of the network, but also our cells, our brain, our organism is a type of a very complex network, or consists of a really large number of different complex networks. So structure is important for us. How we do it in social systems? So we typically map it to two types of networks. We typically study a user network of social interactions, especially this is for online networks. So here, nodes, these plots are actually users, links are interaction between them, whether this is likes, comments, retweets, mentions, whatever you want to study, this is shown through a network, okay? You can have different types of networks. You can have a directed network. This means there is direction from a person to another person. It can be undirected. Usually people think that actually friendship network is undirected, but it's actually directed. There are data showing this. It can be binary. This means that the strength of the interaction between any two people is equal, or it can be weighted, like in the case of friendship, where you have a certain number of very close friends, and then as you add people in the layer of your acquaintances, they become peers, acquaintances, and so on. So this means that interactions are kind of slower. You can also have sign networks. You can have friends and enemies. And this is also quite interesting to study because there you can see different kind of patterns. You can have different layers of networks. So this means that you can have different kind of relationships in the network. So if you have a social network, your friends are one type of networks, your family is the other, and so on. But all of these networks are kind of interconnected, and for instance, spreading of disease, for all of them, it's important to have this kind of information. In the case of social systems that we study online, we usually look also at bipartite networks. This means that we look at networks that have two types of nodes. We have users on one side, and we have posts, comments, answers, and so on the other. So this means we have two types of entities. Usually, these second type of entities are passive, but without them, you would not have an interaction, okay? And this is how, for instance, the social network, I think, on stock exchange mathematics system looks like. So basically, these blue dots are users, red dots are these posts, usually these are questions, and you can actually look at how these networks evolve, and I will show you some of the results in a few slides. What we found out is that the structural properties of these bipartite networks are kind of very important. So while I was doing my PhD studies, we studied emotions, collective emotions in cyberspace, and actually you would see that there are quite differences when you have these networks that have to be used as a bipartite network. They usually are more prone to negative interactions than these typical social networks like Facebook or MySpace, which you would represent like this. I want to show you just a few information from our analysis. So we studied a meetup network. This is a quite popular site which people use for organizing offline events using online means. And also Reddit, which is probably one of the most popular currently news sharing or information sharing websites and discussion sites, and Stock Exchange. All of you know for Stack Overflow, but actually Stock Exchange has like more than 150 communities with similar structure and with similar purpose, but actually on different kind of topics. Here we wanted to understand how these groups emerge. Here we wanted to understand the same thing, but just in online groups. And actually here we wanted to understand what are the properties that lead a certain group to become successful. Why? Stock Exchange has a very open way of creating these communities. Anyone can suggest a community and a topic, but not all of them survive. Actually, more than 30 of them actually died in the process. And we wanted to understand there were, for instance, 2 communities on astronomy, 2 communities on physics, both successful and unsuccessful ones, the same for literature, economics, and we wanted to understand what is the difference between these communities. So we first studied how specific groups grow in this meetup group, and what we shown for 4 different communities. These were on different kind of topics. So these are meetup groups, people who like food and drinks, the ones that like to socialize, people from tech, and outdoors and adventure. So different kind of activities. All of them actually have, all of these groups have this universal pattern of growth. Typically people at the beginning when they join group, they want to spread their connections. So they want to have more and more connections with the people in the group. But as they increase their membership in the group, so increase the participation in the events, they actually tend to more focus on their friendship connections in this system. So this is a kind of interesting thing because this also holds for conferences, for instance. So this is a universal pattern of group growth. What we also looked at Meetup and Reddit is that we actually looked at the distribution of group sizes. Groups founded in 1 year, you can rescale the size of these groups and you will get that everything falls on the same curve. What does this mean is that never mind whether the group was founded in 2007 or 2014, the mechanisms for this group growth was the same, okay? And what we found out is that actually the log rates, so the rates of growth are also universal. There is a difference between the Reddit and Meetup groups, but actually I will show you in the next slide that we can actually look at one model that can explain these differences that we see. So basically there is a universal wave of growth, and we proposed the model that is network-based model, and what we found out is that in Reddit, actually people tend more to follow their social links when they join new groups, while in the case of Meetup in London, this is not necessarily the case. So there is a difference, and actually what we found out is that the model also supports these universalities in the system. And in the end, I want also to tell you about this network, so these communities in Stock Exchange. So there were 8 communities, 2 pairs for physics, literature, astronomy, and economics. these not full lines, they were actually related to groups that died after 6 months or so, so they were closed. They were deemed as unsuccessful by the stock exchange, while these full lines are actually the groups that remained. What this shows is that when you build your own community, you want to help your members to be more cohesive. So this means that clustering in these systems should be higher. So you shouldn't just create these stars, so one person that interacts with other people and no interactions between them. You should promote more interactions between also these other people, in the sense to create more triangles in this system. What is an interesting thing, physics is a quite successful group. It actually became mature and was considered very successful after 6 months. So that's why it's different than these 3 groups. But all of these 3 successful groups, they stayed in the beta phase for several years until they were considered successful. So you can also see these differences in these systems. And to conclude, I don't know if I persuade you, but when you look at your data, think about the relations and think about how you can make these data more simple in some sense. Look at complex network theory that can actually help you to study their structure and dynamics and to search for these universal patterns. And believe me, universal patterns are something that help physics a lot. Some of the Nobel Prizes came from this field, and it actually showed that we can use a very simple model to classify our systems, and then actually we can create more efficient predictive models. Thank you.